We're live. Hello. Let's see. Yeah. Okay. Hello. Uh, yeah. So today we are going to talk about something in game theory. We're going to talk about game theory and programs in game theories. But first of all, let me make sure everything is clean. Let's see. Um, yeah, I think we're good. All right. Hello guys. So today, I think I've already talked about what we're going to talk about in some of the posts you've seen. But before we jump into what we want to talk about, let me just pull this blog by Stephen Wolfram on games between programs. So the whole point is to walk you through or to untangle what he's talking about and talk about some of the ideas and some of the programs that um, are sort of mentioned in the blog, and also discuss what programs are, discuss what it means for a program to play a game, sort of game. We're going to pick a game, uh, any game. It doesn't really matter which game, because it's game theory, obviously, because it's the game that matters, but how to pick the game is what really matters. But so if you haven't read the blog, just find this link and let me post in the chat. I don't know. We don't have no users. Come on, damn. All right. But anyways, so I'll just keep talking until uh, we have enough users to uh, to join us. Let's see what this is. Uh, sure, we're live. What's this? No. Okay. Anyway, so the Games Between program is a blog that discusses some of the ideas we will explore. Basically, what we will do is just run the code and see what games means and what a program means, and which kind of programs we will explore and which kind of other programs um, we can also explore, and how those many or whichever programs you use can play games that we will discuss. So if you haven't read, just keep go and read the blog. I'll just run this first just to make sure things are set up clean, and then right. Okay, so let's talk about games first. Let's talk about what programs are. So in the sense of programs, because in a computational world, programs are in computer science world, programs are a set of instructions you give it to a computer, written in any language, any programming language, whether it's Python, whether you're writing Rust, or whether you're writing C. Those are instructions to a computer to do something, right? Those are like a program set of instructions written in a certain language, and those that a definition of a language is in a computer world is really just the because it's high level language. When you speak in high level language like English or a Python program, you are really talking to a computer, but the computer sees something different. They see bits, zeros and ones, uh, machine code, so to speak. And what what we will be talking about here is another set of view or to a program, in the sense of we are not really going to discuss a program as a set of instruction like a computer program written in a Python programming language, but we are going to talk about a program in a sense of a role. So, and these are like some of the examples we will go through. We go through a finite state machine, a Turing machine, and also a cellular automaton. And if we have time, we can also discuss neural networks, because neural networks are also programs, right? Very sophisticated programs. If you if um, if you have really dug deep into neural nets. But let's talk about finite state machine. So for a finite state machine, what we will see, first of all, let's find out how many, because there are quite a number of finite state machine. But when you're talking about finite state machine, you're talking about how many states that a machine, a finite state machine is usually a simpler kind of program in a sense, and you can represent it in many ways. So given a finite state machine, but let's see how many they are, like, right? So FSM, let's find out how many do we have a function for counts. I don't know. Um, this is SK. So find how many there are. Counts, counts, count. So given S, so we have S. This takes S as a state, and then K is like the number of instructions for the finite state machine. So we say for two state and two K, because we'll talk about what these two means. The two for K means in a bit, but for this case, we only have this number of finite state machines. But for our case, we will explore specific finite state machines that are canonicalized in a sense that we remove duplicates and delete all the other case. So for you say for three states, the number grows as the number of states grows, right? So you can also do for four states, right? Four states we get to 1 million. So for our case, I'll just show you examples of what finite state machine looks like and discuss what those are, right? So we have already canonicalized versions of finite state machines. For two tools, we have a couple of finite state machines, and we can visualize these machines and see what they are. So if I visualize these, we'll see that how they kind of look like in a sense from a view. And from this case, I think what these graphs are saying in a high level language is that given a finite state machine, let's say an example of finite state machine, let's say machine 22, which is or let's pick an interesting machine that we found, that this machine, in game theory, this machine is represented by, it's called Grim Trigger. Grim Trigger is a sort of a strategy that in game theory that um, uh, when you when an opponent when you start a game and then start to play sort of throw your strategy and the other one throws their strategy, whoever whoever the game will start with everyone cooperating, but if you cooperate, if you defect first, then you get punished, right? So what that's like the strategy of Brim Trigger, and that strategy is in finite state machine, the kind of strategy that does that is this machine right here. So this machine, so these are like the nodes represent the states. So you can state the first state here because it's a two-state machine. These will represent the first state and these are the second state, right? So if I say, for example, these are two states, right? This first say the cycled purple just says the initial state, and then uh, um, from the initial state, this whoever you cooperate initially, you cooperate, and by cooperate, the green just means cooperate here in this case. That those are the colors that have been used in the blog by Stephen. So the green one means cooperate, and the red ones means defect. So if you cooperate, initially you cooperate, keep cooperating, right? And the first defector will be the next thing that will happen after that will all the next moves will be defecting, right? You get punished. So this is an example of a green trigger. And you can ask about many other states, right? This is like an example state. You can ask, how about three states machine, right? So for three, let's pick a random three-state machine, random integer. So three states are how many? What three states? Three states are 5,800. And so let's pick a random sort of machine from a so a random machine is this example of three states. So we can visualize that as well. And what we are asking here is how does a three-state machine, a 910 three-state machine look like, right? And this is a bad example. Let's try another one. Maybe this. Yeah, this is a three-state machine. The reason we got the reason this 910, this is why we do canonicalization, because these are two state, but it's a three state, but it's a two state when you visualize it. So when you canonicalize, you get a bunch of a simpler or less machines. But that's like an example of what a finite state machine. And what we will be looking at, that's a program in a sense. That's a program. And let's represent this as a program. So when you talk about a program as a rule, what you're asking is how does a finite state machine look like? And to do that, I can show you an example of what a finite state machine look like. And let's say this finite state machine we convert it to rows. And what we get is a simple rule that represents a finite set machine. And this is like what this machine does in a sense. If you wanted to program it or to use it as a program, you wouldn't use the graph to represent it. You would use this simple example. But so that's like a finite state machine. What about Turing machines, right? Turing machines are other possible programs you can explore when you're studying games, right? And an example of a Turing machine, let's say, let's find out what this takes. So we take a rule, and then um, this is an example of a Turing machine, right? This is a Turing machine, and this is a two-state. I think two. Yes, this is a two-state. Two-state. Yes, this is a two-state Turing machine, right? And what the this if you study these, it just tells you it tells you. If you read this, it tells you what the next move and what the Turing machine should move next and what it will write on the tape, right? And we will use that in our sort of program configuration in the sense that whatever the Turing machine writes is what we will say that is what the strategy of that Turing machine looks like, right? The same way for so how many Turing machines are there? So for a two-state, say Turing machine index, maximum index. So for a two-state, we have only 4,905 Turing machines. And then for a three-state, we have 2.3 million. We have 3 million Turing machines. We can't explore all this. This is a large space in Turing machine, and if you wanted to explore those number of Turing machines, you can't do it with this large number unless you use clever mechanisms to explore that space, right? So we cannot explore those many Turing machines, but this is just an example of a program we can use to study games, right? And then we have cellular automata. So cellular automata is another program that we can use to to study the games in a game theoretic sense, right? So I'll say we have functions in Wolfram language that can plot what program looks like. So if you say for example you give this program, so roll 30, then initial condition, and then the number of steps you want to evolve that roll 30. So I'll just put this here, which says that take a roll 30 as in game in rule in a rule system, rule 30. This is like what it does in visual form. So you start from an initial condition, then you run it for 50 steps, and this is the representation of that what that rule is. Now, those are like example of programs we can use to study games. And what for the neural nets, it's as simple as using uh, an LLM, just asking an LLM to produce a strategy, um, and that strategy will be used as a move for that sort of LLM. We uh, for this case, I think I don't have enough to say about this, but it's something we can study after. Um, and how a question we can ask is how can an LLM make a move, right? Right? How can an LLM or just any AI agent or any AI model make a clever move or make let's say make a strategic strategic move, right? So that's a question one can explore. And it's an interesting question because LLMs are sort of doing stuff, but we don't know what they are doing. Like some people know what they're doing, but if you are a person who have studied neural nets for many years, you will understand what the actual AI agents are doing. But if you do not, then one way to really understand what they're doing is to just let them play games and then see. Because if you define a game, which we'll talk about in a bit. If you define a game, then you know how that game or what the payoff of that game is. But if you feed an LLM a question or a prompt and ask it to produce a strategy, one way to study what it does is to look at what it actually produces as a strategy. So that's one thing we can ask in an LLM. And um, what then can we conclude if an LLM gives a strategy? What then can we conclude that it's an optimum strategy? Like how can we tell that it's an optimum strategy? Um, conclude when an LLM makes a move. How can we how can we tell it's an optimum? It's an optimum strategy. I don't know, like uh, the way to tell if optimum. Yeah. The way to tell if an LLM makes an optimum strategy is you have to define what optimum means, right? For in an LLM world, you have to define what optimum means. And optimum is take for example, you want an LLM to play some sort of or you have two systems of LLMs or agents, AI agents, and you have defined sort of a payoff or um, a measure of what winning means, right? Then an optimum strategy is for an LLM is how simpler or how easy or w- how much does an LLM use or use or how much energy that the LLM uses to produce an optimum strategy, right? That's one of the way you can measure uh, um, an LLM's or a neural net's optimum strategy. You could just ask how much energy did it spend to produce this strategy, and in current LLM or current new systems models are usually expensive in a sense, right? They use so much energy, they use so much compute. But what you want is produce a strategy, but then use as minimum energy or as minimum compute as possible. That's the question you can ask under LLM. But we can talk about that once we have defined what a game is. But for a finite state machine, it's an easy thing to define. Not so many of those are available. For Turing machines, there's a huge space, and cellular automata, there's a huge space to explore. So is LLMs. LLMs are more clever in a sense. They can make uh, educated guesses or they can make they can produce strategies based on reasoning. So that's one thing we can explore in this case. But let's talk about game theory. So we know and have discussed people have discussed game theory and many systems in the current world use game theory as a way of gaining advantage if they're kind of competing against each other. And we see this in governments, we see this in organizations, we see this with even people. People use uh, game theory as a way to guide them to beat the others or to be ahead of everyone else, right? And some people or some organizations or government might not explicitly point out they use game theory as a strategy, but as a way to gain advantage. But it's just a way of studying how to produce the best strategy to gain advantage in a system, or in a system of, what's a good example? Like a good example is um, economic development in a sense. So you are an economist, but then you want to make sure you are ahead of every other economist, or every other government economic system or economic system of government, right? You will use such methods in game theory, and one of the things you will most definitely discover or um, think about is a strategy. So, what is a strategy in game theory? So, strategy is, because we are talking about programs, and programs in a sense of computer programs. Organizations are programs, but they are more sophisticated programs in a sense, because they are led by so many people. And governments is another more very sophisticated program, but it's not as what we want to talk about in sense of programs, because what we are interested in is how can we model such a system of government that uses or such a system of an organization that uses game theoretic methods to gain advantage. So, right? So, um, what is a strategy? So, a strategy in a sense of game theory will be, if my opponent makes a move, right? What is it that what move will I make so that I gain advantage, or my score is always, higher than the opponent, right? So for a program, so say for example you are, let me see, what's the what can I use? Item. So what for in game, a strategy is really just the move, right? The move a program can make. So if you are a program, you are thinking, usually if you're looking at a strategy, you need more information to come up with a strategy. You can't just come up with a strategy blindly. You have no information of how the game looks like, what game are you playing. So you need a game, right, for a strategy. So um, if you're economist, right, a strategy will simply be just, what does the economy look like currently, and who is making more money than I, right? And that to make a move would be like, based on that, what is the best strategy to make, right? So that's like a game. Define a game, define what a move is for a program. And then once you have defined what a game is and a move is, which we'll talk about what a game is and a move is, and you discuss with what what it means for strategy to be optimum, right? Uh, wait, what it means for a strategy to be optimal. So say, for example, you an opponent, or some of the information you'll need is what other moves has the previous opponents, or my opponent, the one I'm facing uh this game with, the one I'm playing this game with, what has they played over the years, right? That's one of the things you will want to know. And then based on that, you can decide what it means for a strategy to be optimum. Because you can't just make a strategy without considering its optimality, its local optimum. How am I benefiting, or how the future of or the consequences of the move that I make currently affects um, my advantage, right? So that's one way to do that. And we will talk about possible strategies and what those strategies looks like in terms of computational programs. And then the other thing is what the history of the opponent. But mostly it depends. It depends on It depends on what? What does it depend on? It depends on the history of the opponent. It depends on what the opponent. It depends on two different questions. For example, do you want is it just the open? Do you just care about the opponent's moves, history moves, or just uh do you just okay, let's see, let's just note this down. So do you care about what the opponent made or the history of the opponent, or do you also care about um do you also care about your moves combined, your history combined together with the opponent's move? Because if you it, how you care about or how you encode the information you receive will determine how you will play. Because you'll say maybe let me care about all of our histories, but then the question um, is that a good strategy to make? Like, will it? Because you can care about the entire history, my history, and the opponent's history, but then there is uh, that effect of introducing noise to your system, and then you make a strategy that breaks your advantage, gives the opponent's advantage. But then if you care about just the opponent's history, then you will have a better um, a better way to know how to beat the other guy, right? How to beat the opponent. So you reduce the noise, but only focus on just what you want to beat. But then that's a problem again because the opponent might just be a larger systems because a big pool of many opponents, and you have to be clever on how to pick which to focus on as information processor. And the other The other thing I think it's interesting, I think in this case will be so given you're given a game, you've looked at the program, you've looked at what what the game should be, and then you've asked what is optimality, what is an optimum strategy. Then you've also asked what is the history of the opponent. What then do you ask after that? The other thing I think you can ask in terms of strategy is when I make this move, right? What what sort of returns do I make? Like, is it what is the score, right? What is this? What is the score? What am I getting out of this strategy? If it's not something um better than what I made before, and better than what the opponent has made, then that's not a good strategy. You have to rethink the strategy. So, what is the score? But those are like some of the things we can look at. But let's talk about what it means for a strategy in programs, right? Program strategy. So for computational programs, what a strategy really means is because we're dealing with zeros and ones, and we saw that for these two programs, um, for example, this thing, FSM, finite state machine, you need the number of states and you need the number of moves, and k represents just the number of moves, right? Right. And one thing you can do is, let's say, for example, a finite state machine, right? As a strategy. And we have seen that for a finite state machine, you need um, S, which is the number of states, because that's the number of states represents just how much how much capability or how much memory you can keep in your system to make a strategy, right? And then K represents the number of moves. So if you ask for an FSM, right, as a possible strategy, and you ask for let's say two state and two moves, right? What is how many are they? There are 64, but they are much canonicalized versions are only 22, I guess. I think. Yes, so 22. So for what you can ask here is for a program strategy, given an FSM, given an FSM, really an FSM just receives because it's really just checking the opponents. Because if you look at an example of an FSM graph, let's just talk about these. So let's say which one is interesting? Take this FSM for example. Um, you start. Let's see, which one do you have here? It's not even showing here. Okay. So we have this, let's say we start here. If you look at this FSM, you can't ask a question or you can't ask this question. Like you can't care about moves of your opponent and care about opponents. So you can't care about opponents and your moves here because it's just telling you what to do when an opponent makes move. For example, starting at this state, this opponent makes a move, let's say corporate, and then what the move you'll make, the nodes will represent what move will you make, and the colors is so because we have k is equals to 2. So if you do 2, we have two moves, but we need to start from, I'll just do this. So these are the possible moves, is 0 or 1. And the green one just represents a 0. And then the red represents 1. So if, say, an opponent makes this move, a 0, produces a 0, then what move will you make based on the previous opponent's move? So this is the previous opponent's move. What move will you make as an FSM, as a 9799 FSM? And it says here you make a red move, right? And then once you make a red move, you go to the next state. And this is state 2. Then in state 2, opponent makes what? They make if the opponent makes a green move, a 0 move, you go back to state 1. If they don't, they make the other move, you go to state 3, and you just keep doing that. It's like you just playing based on what the previous opponents move, right? Now let's take an example. Finite state machine strategy, because we FSM strategy. I think it's called FSM strategy. Yes, and then we say, what does this do? It takes an FSM initial state. Okay, so say we take this FSM, which is 799 and 32, and then initial state. And when you run this, you get a function. But then let's say we take this FSM will take in the history of the opponent. So say, for example, if I was playing against say you were playing against another FSM, say let's pick one other FSM, random FSM, or let's take this guy here, 15. So you were playing against this guy, and this guy made moves previously. So their previous move have has been um, 0. Let's say you've already played a game before, and you made the first round you made 0, and they made 1. Second round you made a 1, they did a 0, and then you keep going. You did 1-1. Now this is the history of these two players. Round 1, round 2, round 3. You feed that to um you feed that to what? To the strategy, and what it produces will be the next move. So as player 1, the next move for this guy, given this history, is a 1. Now that's a possible strategy, right? But suppose you do the same, but for this other guy. So 10, 15, given the same history, let's say as player 1 or maybe as player 2, they say they play the same strategy anyways. That's like a possible strategy for an FSM. Now say we want to figure out how like those two moves um look like when you play them multiple times. So say for example you want to run a sort of a tournament or sort of a game given this initial history and see what the FSM will play um, for all of those for all of those cases. So for example, let's say this is the history. So every time you make a move, you will do so as player 2. Every time you change the history and say we need another random history. Say tuples 0, 1, 2, maybe no, just 2, then 0, 1. So this is another possible history. These are how many rounds are these? So these are uh 16 rounds. You feed that to your strategy, and um as player 1, you get the move they play, and you can ask for all three states. For example, let's take 20 of three states machine, right? um, let's take 20 of these. Then we want to feed it to this machine, right? And then you ask, if I run this history against all these 20 machines, let's see how they look like actually. So these are those 20 machines. And you run this history, the moves they make is zero, like these are the moves they make for each of them. And you can see sort of diversity. Different machines make different moves given the history, the same history. And let's try to visualize. Maybe I'll just do I don't know. What should I do? Damn. uh, 0 to standard red, blue, green, and then 1 to standard red. And then we want to do this. So these are like the moves they make. So it's um, a green just means cooperating in when you're doing prisoner's dilemma. We'll talk about the games later. And then a red just means defect, right? But in our terms here, 0 is red and 1 is 0 is green and 1 is red. Now the other that's like strategies, and it's you can see sort of diversity in this strategy based system, right? And you can ask, maybe let's take the last what 20 the last 20 different strategies, different machine produces different strategies. You can keep doing that. You can do this for Turing machines, you do this for cellular automatas, and you'll get different strategies. Now, that's what a program strategy looks like. Now, the next question I think you could explore is what the payoff, because in game theory, you need the most important bit is payoff, or how do you score a strategy? And it's tough. Like, how do you even decide what a payoff looks like? The good thing is we have already in the Wolfram language, we already have um, different game theoretic data. You can explore different payoffs, uh, and you can read about all those payoffs. And prisoner's dilemma is the most common one, and we will explore that. So, say for example, this is we have this payoff. We have welfare as a payoff. We have yeah, we have so many payoffs to explore. I don't know where's the why is I don't think this guy. Chicken, rock, paper, scissors, prisoner's dilemma, matching pennies. We have so many payoffs you can explore. But um the tough decision usually is selecting a payoff. So you can have different payoff, but then picking a payoff it's a tough decision. So let's say, for example, we take prisoner's dilemma. Prisoner's dilemma as a payoff. So this is a payoff. Let's say we just want the data. So this is an example of a payoff in prisoner's dilemma. And in this game, corporate and defect are the common terms used to assign to a strategy. So you are a player, and you you've been told that cooperating is the best strategy, so you will cooperate. And then if you discover while you're cooperating, you discover that um, defecting, or you switch or you change and decide to defect, then what will happen will determine on what the specific strategy in question is. For Grim Trigger, if you do that, you get punished. The first defector usually gets punished. That's like in prisoner's dilemma, you never defect in Grim Trigger unless the other guy defects first, which means that you get the advantage, right? So that's like an example of payoff. There are so many payoffs you can explore. We have matching pennies. Um, matching pennies is. We also have a chicken. I don't know what chicken is, by the way. Swallow, straight. Then we also do have rock, paper. But rock, paper, scissors is a three moves game. I don't know how do you write rock, paper, scissors? Okay. There are three moves here. So you either you make rock, paper, paper, scissors, scissors. You make rock, paper, rock, scissors, rock. So these are like possible strategies in game theoretic sense. And the question is like how those strategies are scored. Take for example our game, right? So we had these people, these machines playing games. Let's just take the games, their strategy. And these are the strategies they produce, right? And say, for example, um, the other player, okay, let's just produce an example strategy. Um, let's take an example machine, just one machine. Let's say how many machines are there? Okay, let me just take 799 versus 3495, just randomly. Then these machines, how do they look like? Let's say 799 33. Let me use the other one. This is how these two machines looks like, right? Okay, 495. Now, say you give it possible history. So given a history of let's just do four of these. Then history is four, and then you ask let's configure let's just play these two games, right? Um, let's say we want to play, we have two strategies, FSM strategy. The first one is 799 state 22, right? Let's just do with s is equals to 3, k is equals to 2, and you're asking for these two strategy, and the other strategy is module start 1, start 2. So start 1 is that, and then start 2 is FSM strategy 295 SK. And you're asking, given these two strategy, we want to play a game because we know they produce these moves, right? They produce different moves. Then you ask, because we have a function that plays these two things together. So let's say iterated game just takes the two strategies, and then you can produces and then initial history plus number of rounds you want to play. So we have these two strategies and two, and then initial condition is what we had here. Our history is the initial hist. I'll just copy these. Uh, then how many rounds do we want? So let's say we do 10 rounds. Rounds. So you play a game, and these are like for 10 rounds, plus the initial rounds. How many did we get here? So this is um game played, game P. Okay, so for this, let's see how many there are. 14. So 14, that's inclusive of the initial history. So based on initial history, a game or moves are made, and those moves are for each of these machines, right? You take a machine. Let's say let's make this program one, program two, P1, and then player one and player two. And then you're asking, this player one is 799 and player two is 3495. And you're playing a game between those players. So the last move they made from this initial history was 1-1. Then you play the next round. Player one makes move one. Player two makes move zero. The next round 1-1. Next round 1-1. 0-0. Like it's not so obvious that they are what they are what's the word here? It's not so obvious that they are actually doing repeating or periodic. They are periodic in a sense, unless you see it. So let's try to visualize these two. Game history. So game history, we once we visualize this, I think you'll see a sense of. So let's just do array plot this, and you will see like the moves these two players are making. So starts off as, I think, let's make the colors color rules. 0 to standard green, 1 to standard. Oh, because it's because or maybe blue. I don't know, blue and red looks nice. Anyway, so they start with the initial history, which is 1, 2, 3, 4. They start of this, and then the next move depends on the strategy of the game. Suppose we went more rounds than just uh, 10 rounds. When we like, okay, something is wrong. Oh, this is 10 rounds. Let's go 20 rounds. 20 rounds, the game, I think they're still repeating, which means that they're not doing anything interesting. They have found they're like in a periodic sort of state here, kind of just repeating. But that's giving us sense of what a strategy or what a payoff. Oh, sorry, we haven't talked about what playing against a game is. Now, what a payoff does is what we wanted to discover. But given history, right? And this is the history. and you have this, say, prisoner's dilemma. And the question you're asking is, um, given this payoff, maybe we just need the payoff. Damn, what is the payoff? How do I get the payoff? Property, I don't know how to get the payoff. Applications, okay, I think it's here. Matrix, is it matrix? Game matrix? Damn, I forgot. Let me see. Um, payoff array. Okay, it's payoff array. So this is payoff array, right? Okay, from that you get this payoff array. And what you're asking is, I don't know how well to visualize this payoff. I don't think this data set is making sense. Data set. Okay, let's just use data set in this case. So how do you use payoff in this case, right? And it's simple. This is a matrix, right? And each of these boxes represent indexes in the matrix. So for so for this case, we have corporate and corporate, right? So you go corporate, corporate, and you get the payoff for those two. So the first player did corporate, and the second player did corporate. So you get -1, -1. Keep going. Second round, they did corporate and then defect. So corporate, defect, first player corporate, second player defect. The second player has -3, which means that they lose based on, this metric. Now, for to score this, you just need to pass that through this game, right? And then using these, you can get the score of these two players. And to do that, you can just do we already have a function, so I think I'll just um, say this takes the game. Okay, so we just want the game, which is this game, and then we want the history, which is this history. So to score this game, this is the score for each of these player. But we are interested in who wins, right? And the winner, just to explain what the payoff looks is, the winner we can do. Wait a minute. So this is we can total this, or we can do mean of these. We get these, and then maybe subtract. Is it subtract? I don't know. Subtract. Yeah, I think it's subtract, but we need to apply this. And so if you subtract the first one and the second one, if you get a positive value, then the first player wins, right? So in this case, the first player won in this game. If you get a negative value, the first player lost. So here, our first player was this guy who won, who is the winner based on this number of rounds. But a question you can ask, can this player be the winner all through? So say, for example, we go to many rounds, right? So say 100 rounds, and ask, does this player still win after 500 rounds? And the answer might be surprising, but it's interesting that the answer is no. But let's see. Yeah, they still win actually. So say we do for 100 rounds, they still win. 500, 150. Wait, what? Did I? No, 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 no. Did I change? They still win. Wait a minute. I think I have this wrong. Hmm. Um, Main payoff. Which one is the highest? Okay, I think. Yeah, I think we could keep going to 250, um, 500. We want a case where this guy loses, still wins, unless I'm interpreting this wrong. I see, I see. Okay, so let's see this. 200. Ah, I see. Okay, so strange still wins. Oh no. Okay, I think it still wins for those many rounds. But you get the idea. So the idea is you can um you can score these players using a pair of metrics. Now, that's just payoff, and we've talked about the program strategy. But what does it mean for a program to play a game? I think I've already talked about this, but the point is playing a game means just what we've done right here, right? That's what it means for a program to play a game. You have two programs, which is finite state machine two, and another this other program is this guy. And you're asking how does it how does it play a game, right? And to play a game, it just means you take all this stuff we've talked about. We've talked about strategy, we've talked about a payoff, and we have talked about opponents, and take all those into consideration and ask a question: how can a program play a game? And the answer is just take those two and then uh, um, iterate over those every move they make. And then once you get the results, for example, let me take this example here. Mhm. So this is just playing there's different programs playing given the same history, right? But what you're interested in is take a player and then ask the question, if I play a game, give them two players, give them a history, which is the initial history, and then iterate over those two players as they make a move. So we are interested in each of these moves, but then we are iterating over every other player that is playing that game. And that's really just what it means for a player to a program to play a game. And what you will get at the end is let's pull this here. At the end, what you get, let's just go on 10 rounds. At the end, what you get is this. This is what it means for a program to play a game. And if you are, because right now we're just using k equals to 2, right? K or number of states are just 2 here. Sorry, number of moves are just 2, right? Oh no, range 2. Number of moves are just 2, which means that we are only making a 0 move or a 1 move. In Prisoner's Dilemma, you're making it just means you're cooperating or you're defecting. Now, what it means to play a game is just simply iterate given rounds and then two players and an initial history. You play again against those two player, and each round you take what the strategy of these players are, and those strategies are really just what you get or the indexes into the game matrix. Now, suppose you are you don't it's you don't have an initial, you have never played before, you're just starting a game. Now that means for our initial state or initial history, it will be an empty list. You play that, you'll get a completely different result, right? And I think it's completely different, but looks like it's just um well. So this is player one and player two. History and if we go through 20 times and say we do array plot this, I think I have it. Um, Array plot this, you get these two players playing against each other, and then you can score this history like we have done before. Just score it and find the winner. And uh, what game? What is the game? This is the game. Oh, I don't know if we have any chats. So okay, so this is the results of these two players playing against each other, right? And then you can do a total of these, and then you'll get the winner of the game, which is this guy. If you subtract these two, what do you get? Subtract. Oh no. Sequence. Why is it? Okay, it doesn't work. But it worked by just doing this. Okay. Um, yeah, so apply these to that, you'll get, so this minus this. I'm confused. 32 minus 35 minus 35. It's three. So player one wins. Then you can do sign of. So it's a positive, so which means player one wins here. And you do, let's do, I don't know, 2000. Well, 2000 and score them. Player one still wins. Okay. Okay. Um, so that's really what it means to just play a game. Let's try different players. I'll try this guy and maybe a more interesting player. Let's get a player from an evolved player, someone evolved to beat other players, a universal player. Where is it? Was it this one? After 1,000 steps of this adaptive evolution, we get no. There's a universal player who wins against two twos. Is it this one? Yeah, which one is this? This machine. It's a 10-state machine. I will just get this and that's the machine. So this guy wins against all two twos, and we want to find out if that's if they can win against this winner here. So let's say this is player one, and then this is player two, a 10-state machine, and then we want to for player two. Wait, I didn't even change this. Player one, player two. Player two is a 10-state machine, so it's 10 state and 10. So playing these two against each other, we get this, and we can score that. We have the code here. Prisoner's Dilemma, and player one still wins. When does player one loses? Let's see, if I do this, they still win. What if I play this as player one? Okay, oh, yes, stand state. Oh, I see. So this guy loses against 799. So it's a universal winner for two states, but not for this guy, three state 799. Okay, so for two states, let's find out for two states. So given this, we want to do M2 machines, two state machine, and then FM two state machine. So 10 against player M2. Okay, and we just need the history. And for that history, we need to score each one of those and find out if they are actually winners. Yeah, they don't lose. That's true. So it's a universal winner for two states machines. And what this means is each of um, Each of these machines, let's present the machines here. Each of these machines loads against this machine. And the truth I think behind this is because this machine seems to, you know, model the other machines' um, behavior in the sense that the states, the number of states it has so many large number of states, and each of those kind of models or memorizes the two states machines. So with these, every time you play it against two-state machines, it seems to imitate or to what's the word here to model the other the opponent's behavior. And since the opponent's behavior is a simple two-state machine, it seems to do that so well. That's why it gets to beat them. Um, I don't know if let's try to go many rounds and see if still does that. It's maybe 1,000 rounds, and then this, yeah, still wins against 1,000 rounds. Maybe 2,000 rounds. Okay, that's good. 4,000 rounds. It still wins. Uh, even if you go more than 3,000 rounds. If you got 5,000 rounds. I wonder if you got 5,000 rounds, it still wins. So, well, the zeros here just means they draw or they tie in a sense, right? So but it wins more games. It never loses in a sense. So it never loses a single game. And for that, I think that's what it means to be a player who play for programs to play a game, right? For given a program, how can you play a game um, when you define different things, metrics that are required for a game, like for example, strategies, payoff, uh, and how does winning entail, and how do you score a game, and etc. And the other thing is, for example, this universal universal winner. They never lose a game. They draw or win, and they win more than they draw here. I think let's count can count these things. So um, they win more than they draw 10 for they draw against 10 players and win against 12 players. All right, so that's we are time. Okay, so time we only have a few minutes, but let's keep going. What it means for a program to play against another? I think we have seen this. We already answered this question here above, right? But ideally, what it just means is that given an opponent, and for a finite state machine, given an opponent, what will you do? Um, what will be your next strategy um, after you've seen what the opponent has done? And we have seen this from our exploration here, and it's clear that this is damn what happened. Let's just keep this here. Oh, so many rounds. Yeah, so given, let's add frames mesh to mesh style, gray line. I don't know, maybe that. Okay, gray level. All right, so program play against each other. This is really just what it means for a program to play against another program. And I think it would be nice to show what a grim trigger looks like. Where is that trigger? This guy. So playing a grim trigger against all the other two machines, we will get, let me say, map. No, no, no. I don't just need this. M M2. F7, and then M2 should be um, we need machine 2 helper. Then machine player 2 should be here. And then this should be a grim trigger. This should be M2. You play a grim trigger against, because there are two machines, against all other machines for in 2-2. And what you'll get is G is there, right? This is what you get when you do play a grim trigger against all two machines. Now let's see who actually got punished really who got punished more, and does it win against all machines? So let's take these and find out if Grim Trigger wins against all these. So Grim Trigger loses against, which one is this? Um, this is position 1, 0, 1, 2, 3, 4. So FSM position 4. 20. Wait, how does it loses against 20? What 20? Oh, interesting. Okay. But point is that when you do when you play a green trigger against all two twos, let's find an instance where the other one got punished, which is this guy. So they start off by the green trigger start off by cooperating, then the opponent defects, then what it does is just defect, just punishes the other opponents for betraying the game, betraying them. Same thing for this machine. This this um this. So the okay, I think this got punished, but they happen to win because they defect always. That's why 20 wins, because it defects always. And I'm sure there's another one which is this. Which one is this? 8. 1, 2, 3, 4, 5, 6, 7, 8. Not this. Really. Yeah. So it's a punisher. Like this strategy is a punisher. Grim Trigger is a punisher. But let's see, Grim Trigger. So Grim Trigger is for repeated game. Initially, player uses Grim Trigger will cooperate, but as soon as the opponent defects, thus satisfying the trigger condition, the player using Grim Trigger will defect for the remainder of the iterated game. Since a single defect by an opponent triggers defection forever, Grim Trigger is the most strictly unforgiving of strategies in an iterative game. So we found that to be true in this case. It's unforgiving. It doesn't forgive betrayal. So, um, and there are other strategies we can talk about, but the point here is that what we just need to find out how does a program look like, which we know that we can explore that by, exploring finite state machines, which are role-based or graph. You can visualize that from Wolfram's post. This is from Wolfram's post, the graphics. And then you can also visualize from Wolfram language other games like Turing machines. Let's see an example of Turing machines, a Turing machine example, and that is this. But okay, I think a good example is how do we select a Turing machine strategy? So one-sided Turing machine is the case we'll explore here is Turing machine plot. I think it's plot. We can do one, three state, two state. Say we want to given let's define a strategy, an initial history, which is tuples, and that's too many. That one, and then from this we can get what happens is we decode this into an integer and pass it to this. So say if it's integer 7, number of damn, that's slow. Uh, that how comes this? Let's find a Turing machine. A good Turing machine. Maybe these. These. No. These. No. Okay. I don't know which. Uh, non-halting, unique. Oh, I see. This is 2, not two, not. I need two twos here. Awesome. So this is an example of. Okay, I need to decode these two. Let's flatten this thing and then change it to from digits base 2. So given this as an input, and we run it for many steps until it halts. So when it hits the right bar, the machine halts. And what it means for strategy in for this Turing machine is let's go here, Turing machine TMs. This is what it means for a strategy. So check at the point where the machine halts, and then pick um, the last move it made. So which is this guy. So it made a defect move or a 0 or a 1 in this case. So keep doing that for all Turing machines, and I can try to, I don't know, maybe take a few unique Turing machines to choose, take 10, and this will be TM, TM. Um, this will be, so this guy made we can do this one. This guy made corporate defect, corporate defect, corporate defect, defect, corporate defect, corporate. Look, they are making different strategies every time given the same input. But that's just what it means for Turing machines. And we have talked about such programs as Turing machines. We haven't touched cellular automata, but it's the same concept. We also haven't touched neural networks, which I think will be an interesting um, case. And this exploration uh, is sort of giving birth to the concept of agents communication, or sorry, agents competition. So maybe you have agents and you want, out of those agents, you want to select the best agents to do the job. One way you can do that is play games, right? Selecting the best agents to do the job or to perform to perform a task. Um, you play a game, but it has not been defined what that game might look like, right? That's the big question. Like how will that game between agents look like? How can you even construct a game matrix, or how can you construct a strategy is easy because agents are smart. They reason given input. But then the big part is how to define uh, a payoff um, or a game in a sense. If it's a board game, it's an easy thing, right? Um, um, Machines have learned to beat that game. But in game theory, defining a game is a hard task, and you have to consider so many variables. And in agentic world, those variables are hard to come by. Like it's we know it's not clear. Um, if we define a game, we need to know whether agents are doing well, right? Right. So agents are doing well. We need to know that. And how do we know if agents are doing well we if we have a flawed game, or if we don't have a better payoff matrix? So we cannot we cannot play it, we cannot determine, or we cannot design a better competition environment for agents unless we have a better payoff matrix, or we have a better way to score those agents, right? So we can't really um, define what um, competition really looks like in agentic world AI agents without actually without actually having a better payoff matrix, deciding, deciding a better payoff matrix. um, or a better game. In a world for example, an example of something that I've been working on is you have a tool or a coding system where agents coordinate and program, do those kind of cool stuff, and you vibe it, you talk to it, you tell it to do something. But usually, what they produce is they can produce a system that actually works, but go and read the code or just check or try to yourself code it or fix a bug or do um, uh, all sorts of things like try to figure out how to help the agent. It's quite hard because the code usually most of the code that is written by so many agents right now is so bad in a sense that it's not readable in a sense. It's not comprehensible. You can't come to tomorrow and read code that is written by an agent and be like, "Oh, I get this," right? It's really hard. So to solve that, we need better toolings in the sense that agents can talk to each other, write better code, because we don't have there are some systems that have tools that score agents code, but there's no actual better scoring metrics. I can show an example of what I've been working on. I don't know if I have it opened. Let's see if I have it open. I can open it. Can I? No. Where is it? Okay. Let me just show this example. So this is a tool. Okay, so the point is, how do you score a agents output? Like you have agents. This is the same problem we have discussed here, like designing a payoff. How do you score agents output? And in coding world, the output of an agent is just a diff of what they are writing, the code they are writing. You can't score reasoning in the sense that it's so hard to score reasoning because we can't even ourselves score reasoning. There are metrics to that, but maybe for agents it's hard to score that. But for code, it's easy because you can just score the diffs. But then coming up with a scoring function, like a payoff in a sense, is quite hard. And games between programs is sort of a path to, designing better um, fitness functions for agents to score code. And out of that, I think um, this tool, if you're interested, I think it's one of those tools that um, what those tools that uses these methods of competitions to score agents, right? So you have agents running. So I have these agents running here. Select agents you want to run, and here there's functions or there are, statistics. So these are like you encode code as a structure as a payoff function, right? You encode code as a structure. So this is a structure. Code is structured in this sense, and you can see the structure right here in this case. And if I flip these, let me just flip. If I flip these, you'll see how the structure looks like. And I think I flipped the wrong one. Okay. Uh, in any case, the structure is encoded, and that squad structure is fed to agents every time they edit this file or any file. It's so abstract. There's ways to feed agents this information, and that's how they get the information of um, the code they have written, measure their code through that fitness function. And one way NEAT does is let's just run a simple simulation of this structure. So this is like a simple this died out for quickly. That's not good. Which one is this? Anyway, so you run a simulation of that structure. The agents do the same thing, and then what they produce is what this produces is a genome of that the lifetime of that specific edit the agents did to the file. But that's just one example. And um, the feature for this sort of games between programs or how programs can play games with each other is really in how do you even decide what game they should play. And I think the research that should be done is answering those questions, like how do you design the game? How do you design a game for agents? Because games are interesting, but then designing a game requires you to think about questions like how do you score, what does what agents see, and does that help them in a sense? And that's like what we are like mostly focusing on. And we are building tools like Neat. Neat is terminal based. You can do many things with it. And you can score agents code. You can um, write code with the agents. You can play games with the agents. So it's one of those directions that um, will lead us to discovering what scoring agents means, or what agent competitions really mean. And I think we've done a lot, and we're out of time. But thank you for watching. And if you have questions, let me look at the chat. So uh, what are you? What's like his strategy? Um, so Cody asks, what are you copying? Like his game strategy? Well, if the question is about um, I don't know if what I'm copying, or what the agents is copying. I believe it's just if the question is regarding programs and what they are doing is like the strategy of a game, or copying his game strategy. I don't understand that question anyway, Cody, so I'm sorry. Uh, no other questions. Hmm. Okay. So I think that's it for today. Thanks, thanks guys for watching this stream. And here.